All right, so today we're going to be learning about torque, right? Because it applies with the levers that we were talking about in our previous class. So, for example, here I have a lever, right, with Garfield and Nodi, right? And they're each supplying a torque. Now, a torque, right, is just sort of a force which causes something to rotate. Okay, now we talked about the door, right? You apply a force on a door when you push it open, but also where you apply that force will also depend on how strong that rotating force is, which we call it torque. Okay, so it's also important as to where you apply that force. So here's an example of our door. Right? If you apply the force a short distance from the hinges or the fulcrum, its rotating axis, right, then you need to apply a very large force in order to get the same torque as another door where you apply that force a very long distance away from the fulcrum. Right? We all know that it's easier to push the door if you're applying your force further away from that rotational axis, from the hinges. Okay, and usually we apply it at 90 degrees. And in this class, all of our forces are going to be applied at 90 degrees. We're not going to talk about angles. So, in that case, torque will need to be considering two different things in order to calculate it. One, the force that you apply, and two, the distance between that force and the fulcrum. So our equation will look like this. Torque, which we're going to label as capital T, equals force times the distance between the force and that rotational axis, or the fulcrum. Okay, so here's our equation, and although they are vectors, we're not going to be considering the direction in this course. And we're only going to do examples where the effort force is perpendicular to that radii vector, right? The radius vector d. And therefore the torque is also perpendicular. Now the units, the unit of force is newtons, multiply the unit of distance in meters. Torque doesn't have a special unit all on its own. We simply say Newton meters for the units of torque. All right, so let's try some practice problems with this equation. All right, so question 1. A mechanic applies a force of magnitude 540 newtons perpendicular to a wrench to loosen a nut. Calculate the magnitude of the torque if the distance from the applied force to the nut is 30 centimeters and 50 centimeters. So with the same force, using different distances, how does that change the torque? Let's try with the first one. Torque with our equation is just force times distance. Our force is 540 newtons. Distance is 0.3 meters. Remember to keep it in meters, not centimeters or anything else. And we get a torque of 162 Newton meters. If we do the same thing for 50 centimeters or 0.5 meters, do force times distance. Force is the same. Distance has now increased, and with an increased distance, we get a greater torque. All right, so let's move on to question 2 then. On the back. Not question 3. There we go. Question 2. So we have a corral gate is partly open. A cow hits the gate with her head at a distance of 3.6 meters from the hinges. So D is 3.6 meters. If the torque produced by the cow has a magnitude of 540 Newton meters. So in this case, they're telling us torque, 540 Newton meters. What force did the cow apply to the gate? Now, if we go back to our equation right here, we can write a triangle to help us. Right, where we'll have torque at the top, force, and distance. Right, so in this triangle, for this question, we're trying to find force. So force will equal torque divided by distance. Right, so go back to the question, and I'll write force equals torque divided by distance. Torque is 540 Newton meters, and distance is 3.6 meters, which gives us a force of 150 newtons, which honestly isn't that much. I expected more from one of these bulls, or sorry, cows. All right, so let's go and apply what we know about torques to what we know about levers. So here's an example of a lever. This is a first class lever, if you remember. Fulcrum is in the middle. Then we have a force on one side and a force on the other. Now when you have a force acting on a lever, and a lever is something which can rotate, they're each applying a torque, meaning they're each trying to rotate the lever. This effort force is trying to rotate the lever counterclockwise, and this load force is trying to rotate the lever clockwise. Right? The effort force would be equal to, the effort torque would be equal to that effort force times the effort arm, right? The distance from the fulcrum to the force, that's the torque. And the load torque would be equal to that load force times the load arm, which is the distance from the fulcrum to the load. Now, if one of these forces is greater than the other, for example, if the effort force is greater than the load, I keep saying force. If the effort torque is greater than the load torque, right, then it will overcome that load torque and it will rotate. It'll win and rotate counterclockwise. If the load torque is greater, it'll rotate clockwise. But if the effort torque is the same as the load torque, it won't rotate at all, and it will remain in what we call static equilibrium. Okay, so this we call the law of the lever. So when a lever is in static equilibrium, the effort torque equals the load torque, and it will just remain in its position without rotating. We can write this as an equation, right? Because we know how to calculate torque. It's force times distance, right? But if we know this lever is in static equilibrium, we can say effort torque equals the load torque. And we can use this to solve certain problems. So let's use this static equilibrium law and do some questions. Question number 3. So here you have a camper wants to mount a trailer on blocks for the winter. One quarter is lifted by applying an effort force using a 3-meter steel bar. Right here. So they're saying this steel bar is 3 meters. The block is 45 centimeters from the fulcrum. Right? So that means this block, there's your fulcrum. So this distance here is 45 centimeters, or 0.5 meters, and provides a load force of 1,800 newtons. So this is called our load arm, and our load force is 1,800 newtons. Okay, we need to determine the effort force. So right here, what's that effort force? Now to do that, notice that this 3 meters is not the effort arm. It's the length of the entire steel bar. The effort arm is from here, the fulcrum, to here. Now if we know the whole thing is 3 meters, and we know this portion is 45 centimeters, we can say that the effort arm is 3 meters minus that 45 centimeters. 2.55 meters. Now that we know that, we can go to our torque equation, where our effort torque equals our load torque, and torque is force times distance. Right? And we know everything here except for the effort force. So if I divide both sides by that effort arm, we get the effort force. Right? Those will cancel, and then we can substitute what we know. This is 1,800 newtons. Our load arm, 0.45. Our effort arm, 2.55. We get an effort force of 318 newtons. All right, moving on to question 4. So this one, it says calculate the effort force for the situation shown using the law of the lever. The law of the lever is just when the torques are equal so that they're in static equilibrium. And so here we have an effort force, here we have a load force, and here we have a fulcrum. So now the fulcrum's not in the middle. The load force is in the middle. So this is a second class lever. Remember the definitions for what your effort arms and your load arms are. This here, from the fulcrum to the load, is your load arm. And that, they tell us, is 0.8 meters. Okay. The effort arm is from the fulcrum. It's always from the fulcrum to the effort force is your effort arm. That is not 1.8 meters. That's not 1.8 meters. Or 1.6, sorry. Can't read that. Okay. 1.6 meters in this diagram is from the load to the effort force. If we want to know what this is, we need to figure out what that total distance is. So it'll equal 1.6 meters plus 0.8 meters, right, which is 2.4. So always make sure you figure out what those effort and load arms are before you start punching things into your equation. Now the load force here tells us is 640 newtons. But what I could do in a question is not tell you the load force, but instead I could tell you the mass. Right? And the load force would just be the weight of the object. So you would take the mass, let's say it's 64 kilograms, and you would multiply that by 9.8 newtons per kilograms, right? F equals mg. So that's a good thing to also be aware of. Okay, but in this case, they tell us what it is. So we can take our torques for our effort and for our load. Okay, so now we know everything here except for our effort force. So divide both sides by our effort arm. And we can calculate our effort force. We have our load, which is 640 newtons, times our load arm, which is 0.8 meters, all divided by our effort arm, which is 2.4 meters. So that's going to equal 213 newtons.